Hello, this is Pranav Poduvai, a senior data scientist at Mastercard's AI Garage. I will be presenting on the topic cache via optimal diversity for ensemble learning. Cache stands for Combined Algorithm Search and Hyperparameter Optimization. It is of critical value for Mastercard and I believe many other companies that work in the domain of tabular heterogeneous data. Because as our data drifts and as there are new patterns that arrive in our data and we would like to capture those, it is a wise strategy to automate our entire step of algorithm selection and hyperparameter optimization so that we can ensure have some performance guarantees. Otherwise, it kind of depends upon the motivations of the data center and how motivated the person is to find stuff and look at the patterns in the data and make the changes accordingly. So, if it helps in maintaining a standard of quality, it helps in speeding up the deployment timelines, and it saves our time. Again, if we are able to deploy our products faster, we are going to time is money, so we will be saving a lot of dollar value. That is why cache in general is a very important problem to be solved. So now let's just talk about how we go about solving it. Cache is usually solved. The prior cache approaches use a Gaussian process surrogate for kind of modeling the how our model will perform in the holdout validation set, and we try to find new configurations using the surrogate function, which may or may not perform well. As in when we explore and exploit, we kind of find new and new configurations suggested by our surrogate function. So if we look at the leftmost side, that is the target of most of our surrogate function. A traditional Gaussian process, it is usually fit for like it could be mean square error, it could be mean absolute error for regression, for classification, it could be accuracy, it could be the cross entropy, it could be Brier score. All of these depends upon your what your goal is and what your product is. And so the upper left hand side is how like most traditional cache approaches solve this problem. How are we different? So what our observation was, the optimal solution is usually not a single model, and it is usually an ensemble of the different configurations that have been observed so far. And if I was able to observe that we can kind of decompose the ensemble loss or ensemble generalization error for most traditional losses into an individual performance metrics and a pairwise diversity matrix. And if we have a look at for particular mean square error case, it is like the covariance matrix of the errors. And for cross entropy, it's a slightly more complex. But again, it is just dependent upon your target or your labels and your current model, how well it has fitted. So kind of it depends upon your errors. So what we observed is this misalignment. So most traditional models just try to minimize the individual performance, and which is kind of misaligned with our final objective of minimizing the ensemble error. So how do we go about solving this? The most trivial way is use another surrogate function which can model this pairwise diversity. So if we kind of these are independent metrics, so we can train a separate surrogate model for the individual model, a separate surrogate model for the pairwise diversity metric, and then we can combine their acquisition function. Get the acquisition function, which could be a Gaussian process, lower confidence bound, or expected improvement. Like there are many options available to us. We get the acquisition function for our traditional GP, we get the acquisition for our diversity surrogate, and it will be a weighted combination of these two. That will be our true acquisition function, out of which we'll be sampling the next configurations. And if we are able to do that, we'll actually be minimizing the right hand side of this equation. And by minimizing the right hand side, we are guaranteeing to be minimizing the ensemble generalizing loss. So I would say that is the entire core and crux of our work. We observed a misalignment of prior cache approaches where they are trying to minimize solely the individual model performance, and they haven't looked at ways to directly minimize the ensemble error. And our approach is trying to fix that. Yeah. Thank you. Thanks a lot, everyone.